So in this lecture we're going to go through the theory of what's called least squares curve fitting, something like this. So suppose you have a set of data. Now the data is your data points given in terms of an independent and a dependent variable. Usually this is something you control, so you change the values of x and you make measurements of y at the corresponding values of x. Now what you're trying to imagine is that all of the data, all the measurements contains errors, but there's no reason for the errors to be all positive or all negative. You would expect that they're the errors are random. And what you're trying to do is, given the data, which is all the data points, you're trying to say that maybe the data comes from that the true values lie on a line, and so all the data points are made up of the true value plus an error. So I might just draw some of these little errors here. So that would be a little error there. So here the data appears to have a linear relationship. Well, this is called affine relationship really. So it's like y to mx plus c. Perhaps the measuring process was not precise or accurate. Is there a line of best fit for this data as shown? Is there a theoretical true behavior as represented by the true line? What we might write down is that the y value is equal to, well, I should use the big Y, ax plus b, which is really like mx plus c plus a random error. And these are the errors. Actually, I'll change from this funny letter here to this delta. Okay, so the question is, what does it mean for a line to be of best fit? And there's different arguments about this. You might, if you did maybe some physics at Leaving Cert, you want to say, oh, the line gets an equal amount of data points above and an equal amount of data points below, but it's a bit more involved than that. So if I say these are the errors, so say this is like delta, well, if I go here, delta 1, delta 2, these would be the errors. Delta 3, say, for argument's sake, this is delta 15, something like that. Or a general one, it's just you might call delta I. So let's look at this error here. So the difference between the imagined true value and the measured value. Let's call this delta I. So one way of doing this would be, could I find a line that minimizes the sum of these errors? Now this error is positive and this one is negative, but you take the absolute value. So could you find the values of a and b? So different values of a and b give you different lines. A is the slope of the line, b is where it cuts the y-axis. So the question is, could you maybe find a line that minimizes the sum of the errors? And I think if we try and draw the line by I, just using our eye, that's probably what we try and do. Now we need to write this down mathematically. So what I'm going to do is I'm going to take, say, this here will be the point xi, yi. And then, so directly underneath this we have xi. And so if I use the y equal to ax plus b, I would have that the coordinates of this point down here on the line would be xi axi plus b. So the error would be the difference between yi, which is something you've measured, and axi plus b, which is what you predict is actually the true value. So this approach would say you want to find the values of a and b. That basically means the slope and the y-intercept that minimizes this function. So this is a function of two variables. This is going to be the sum of the errors, and it depends on two things, the slope and the y-intercept. Once you specify the slope and specify the y-intercept, that gives you a specific line, and you can go away and calculate the sum of these errors. So it's a function of two variables, two numbers in, a and b, one number out, the sum of the errors for that. So this error here would be the difference between the y value and the axi plus b. That's what we have here, yi minus axi plus b. And we take an absolute value because, as I said, some of them are negative and some of them are positive. I want errors to be positive. So this function, if you want to minimize this, minimize the sum of the errors, that means kind of getting the line close to the points kind of all simultaneously as such. The problem with this is very, very difficult to analyze. So to actually solve this problem is difficult mathematically. There's other issues about it. It doesn't give a weighting to particularly large errors. So you can have loads of small errors kind of balanced out, well, not quite balanced out, but and then a really, really big error, but maybe a really, really big error should count more. So one way that you can resolve these issues, and you can be a bit more precise than I'm just saying, oh, I can't solve it, and oh, it doesn't do this. Okay, one thing you can do is something that you can do that you can solve the problem, you can find the line of best fit, and it'll make so an error of twice as big count to 4 as much, an error 3 times as big count 9 times as much. Now it needs a bit more justification than that, and if you really want it, you can Google why do we do least squares. But this is what I'm proposing. This one is easier to analyze and also magnifies the effect of large errors. So here we have the sum of the squared errors here. So we want to minimize this. Minimize the sum of the squared errors. And these are the squares. So minimize is like least squares. So when you find the line of best fit, it means the line that minimizes the sum of the squared errors, the sum of those squared deviations there. So the question is, how do we find the maximum of this? Well, let's see what we do. Okay, so we need a little bit of stuff from last semester, which is functions of several variables. In particular, this is what we're going to be looking at. We have two numbers in, which for us are going to be a and b, and one number out. Okay, and you can plot this function. I think we're going to do this in a second. So the data you know, by the way, so xi and yi are specific numbers. We're going to see this, and we're going to plot one of these functions and say, oh, we want to find the minimum of it. So as an example, consider this data here. So the data is x equals 0, y equals 1, x equals 1, y equals 3, 2, 5, 3, 8, 4, 11. So these are the x1, y1, x2, y2, x3, y3, etc. So the x and y are data. This data can be plotted, and we can try and fit a line of best fit. So let's see, at x equals 2. So if you're saying that this is y equal to ax plus b, and you're putting in x equal to 2, it'll be 2a plus b. That's what the line will predict. So the prediction here for what's going on at x equal to 2 using this line is 2a plus b, but the measurement is 5. And the difference between them, 2a plus b minus 5, that is the error, delta, what we might call delta 3. So the difference between them is the error. Okay, so let's try and write down the function that describes for a general line the sum of the squared errors. So, okay, so the first one, the measurements, so we'll just notice the measurements first. So they're the y values, the 1, 3, 5, 8, 11. So putting all these in. Now remember, this just means add up. So the y, let's just focus on the y. Look, here are the measurements, 1, 3, 5, 8, 11. That's fine. And minus, now this thing is, now really what's going on is it's minus ax plus b, but if you take away a sum, you take away both of them. So these are the predictions according to an abstract line ax plus b. So I sub in the x values, 0, 1, 2, 3, 4, into ax plus b. So sub in 0, sub in 1, sub in 2, sub in 3, sub in 4. And then it's the squares, so you square the difference between the measurements and the predictions, square them, and then add them up. And if you multiply this all out, you get this kind of complicated function here that depends on a and b. Now our job is to make this as small as possible. That's kind of tricky, but with the help of a picture, maybe we can understand what's going on. So this function can be plotted using some software. So at each coordinate a, b, we have a height. So I think it might be hard to see, but like say for values of a equal to 20, b equal to 30, you got a large sum of squares. But somewhere down here, there's a value of a and b that makes this sum of the squares really, really small. In other words, like each coordinate a and b, this corresponds to a line. So each point pair AB gives you a line y equal to ax plus b. And we want to find the pair a and b that minimizes the sum of the squared errors. In other words, we want to find the line that minimizes the sum of the squared errors. Now the question is, how do you find the minimum? So you need to use some stuff that you know from last some, well, a little bit of it. So look, this is kind of an exaggerated version of what's going on at the bottom when this bottoms out. So we want to find it to be, what is a minimum here? Well, it's kind of like a minimum with respect to, say, A, and it's also a minimum with respect to B. So what I'm getting at here is, I think you can hopefully understand there's a peak here. So imagine the peak of a mountain. If you slice it down in one direction and look at the cross section, you got a curve, maybe a function of A. If you cut it in the other direction, you get another curve, a function of B. And what you want to do is find the top of it will be a minimum with respect to both A and B. And I think we said in a very previous lecture, how do you find a minimum? It's where the derivative is 0. So this might represent, this is flat, and also this is flat. So this might be in the A direction, this might be in the B direction, and we want both of those derivatives to be 0. And it turns out, so you get minimum where the derivative with respect to A is 0 and the derivative with respect to B is 0. And for a minimum, we would have mentioned this last day. How do you remember this? Well, this is a plus ax squared, and this a is related to the second derivative, so for a minimum you want a second derivative to be positive. Okay. So this is to be compared, yeah, okay, so something we saw previously. The minimum is where the derivative is 0 and the second derivative is positive. Now it turns out, for the data we looked at, that if you solve both these equal to 0, so what's this? Differentiate this with respect to A, let it equal to 0. Differentiate this with respect to B, partially, let it equal to 0. You get simultaneous equations in A and B which you can solve. And it turns out that the value of A and B is 5 over 2 and 3/5. I don't know if we can actually see that from the picture. Hardly. I mean, it's like 5 over 2 and 3/5. It's, yeah, not too bad. Right. Now, what we're going to do actually is we're not going to explicitly write down that function of A and B, because otherwise it makes the problems very, very long. So what we're going to do is we're going to kind of, this is just a theory lecture, so we're going to show you the theory behind the formulas that we're going to use, basically. Okay, now I'll go over this reasonably fast because it'll be quite tricky. So let's say if I have, do I need to write down? I do have to write it down again. So the sum of the squared errors, S of AB, is equal to, add up, it was yi minus axi minus b squared, and you're adding up over the data points. So differentiate this with respect to b. Now, first of all, it's a sum, and you can differentiate a sum term by term, so the sum can just stay there. Now we're differentiating this thing. Now, if it is just, say, b squared, it's no problem. But it's not, it's a function of b squared, so we need to do the chain rule. The chain rule says you differentiate the outside. Now the outside is x squared, so maybe I'll just do a little bit of writing here. So I'll just write it over here, just so you see what's actually going on. We're trying to differentiate yi minus axi minus b squared using the chain rule. So the chain rule says you differentiate the outside function. The outside function is x squared. The derivative of x squared is 2x. The chain rule says evaluate at the inside. So that's yi minus axi minus b. And then the chain rule says you must multiply by the derivative of what's inside. Now what's inside here is yi minus axi minus b. Now if you remember your partial differentiation, this means only b changes, everything else is constant. So yi is a constant, so the derivative of a constant is 0. axi, they're all constants, so the derivative of constant is 0. And finally, the derivative of minus b with respect to b is minus 1. So you end up with 2 by this thing by minus 1. So this is where this is coming from. Now we're interested in this equal to 0. So we do some messing around here. I think it looks like I multiply this out. Do some messing around. You end up with this equation here. Okay, so this is one of the equations that must be satisfied by a and b. Remember, a and b just means a line. That the derivative with respect to b is 0. Now we also need the derivative with respect to a is 0. And if you do a similar story, chain rule is slightly more complicated, you end up with this equation here. So you end up with simultaneous equations in a and b. Now remember, the x and the yi, it should be a little confusing looking at it, but in a question they're actually going to be numbers. They're going to be actual data points. So this is a number, x is a number, x by y is a number, x squared is a number, x is a number. So this is actually just two equations in a and b. Okay. Now one of the things we might say here, probably set it up for later. So this is a. Now this means add up, and it's x is changing. So it's ax1 plus ax2 plus ax3 plus ax4, etc. Now a common factor in all of those is a. So if you take out the a, you'll have a times x1 plus x2 plus x3 plus x4. So that's the same as a times add up x. Now we'll probably leave talking about b, add up the b, to a little bit later. Similar story, we can take out the common factor of a here and the b here. You can take out the common factor of b, but it'll be b times add up 1, which might confuse us a little. Okay, so these are what are called the normal equations. Now what you'll want to do, this is only for a line, we'll actually be fitting other shapes. You want to be able to see the relationship between these two. So I'll just show you how this actually works. So once you figure out the curve you want to fit, in this case ax plus b. Okay, now I'm going to use this twice here, but anyway. So what you do is you're going to have data given in terms of x and y, and you want to find the a and the b such that this line fits the data as good as possible. It minimizes the sum of the square errors. So how you do it is you think of the two things that you're looking for, b and a. Now first of all you ask, what's b multiplied by? And b is actually just multiplied by 1. And what you do is you multiply everything by 1 and you add up. So if you multiply by 1, it makes no difference. So you add this up, add this up, add this up. That's how you get the first equation. And then the other one is what was a multiplied by x. Multiply everything by x. So you get xy. X by x is x squared plus b by x, and add up. Now we will cover that again when we get there, but that's when it says what is the relationship between the two of them. You get the first one essentially by multiplying everything by x, but it comes from the original y equal to ax plus b. Now there's a little remark if you want to understand a bit further. There's another way of talking about where these equations come from. There's another way of thinking about least squares, but I'm not going to cover it. But if you want to, you can read it. Okay, so that's the theory, and now what we're going to want to do is do some do an example.